Hello friends, welcome to the session on strain energy problems. So today we'll take problem on a frame. Determine vertical deflection of point C. E is given as 200 into 10 200 kilonewtons per mm square. I 30 into 10 raised to 6 mm raised to 4. We have to find vertical deflection of point C. This is the frame cantilever portion. For that it is bent like this. 1 kilonewtons is the load applied. These are the distances 3 and 4, I, 2I. I have to find vertical deflection of point C. Now just let us see how this frame bends. If this is my frame, when I apply the load, it is going to deflect like this. So this distance will be vertical deflection delta. I have to find this. Now to solve this, what we have to do is we have to draw the free body diagram of this bent frame. So free body diagram means what? You remove all the supports, you remove all the joints and apply the equations of equilibrium for each joint and each of these members. So first let me separate all the members. This is how it will look. I am going to separate this member BC and AB, remove the supports. Now for this, apply the given loads. Now your given load is 1. Kilonewton. First, let me apply equations of equilibrium for this vertical load. When I want to make this member BC in equilibrium, I have to write summation V is equal to 0. Summation of vertical force is 0. So, at this end, to make summation V is equal to 0, I should apply a force equal and opposite to this to make this member in equilibrium. So, here I am going to apply 1 kilonewton load. Now, if you consider only this much member, summation V is equal to 0 is satisfied. Now, come to this joint portion. Also, this joint should be in equilibrium. For this joint also, I should be able to satisfy the equation summation V is equal to 0. So, here 1 kilonewton upward is acting. At this end, I should apply 1 kilonewton downward, so that at this end summation V is equal to 0 is satisfied. Now come to this member. Forget this part. Consider only this load and this member. To make this in vertical equilibrium, I have to apply 1 kilonewton load equal and opposite at this end. So this makes whole structure in equilibrium for point loads. 1 kilonewton, first consider this section, BC section, 1 kilonewton here. At this end, equal and opposite to this, summation V is equal to 0. Now consider this joint, this is acting. For this, apply equal and opposite this. Now, to balance this, apply this equal and opposite. Hence, this whole thing is in equilibrium now. Now, let us consider the bending moments. At this end, what is the bending moment acting? Because of given loads. Because of this load into distance, this distance is 3. Bending moment at this end is 1 into 3 kilonewton meters. It is going to act in this direction. Now I have to apply a force, a couple opposite to this, so that its value becomes 0. Summation M is equal to 0 is satisfied for this section BC. So equal and opposite to this, 3 kilonewton meters. When I apply this, its couple is balanced here. Now I have balanced moments for couples for this section BC. Now I have to balance these sections or couples for joint B. This is the anti-clockwise acting. So at this end, apply opposite to this clockwise. Clockwise, value same, 3 kilonewton meters. It means this joint is in equilibrium now. Now consider the section AB. At this end, 3 kilonewton meter is acting clockwise. Apply 3 kilonewton meters anti-clockwise. Now this frame is in equilibrium for point load as well as for bending moments. Now I am going to write equation for moment x for each of the sections. So to do that, I am going to write a table which will simplify the things for me. Portion means beam. So first CB, BA. Next I am going to take section, origin of the section, limits of the section, bending moment x of the section, EI values or rigidity values. Now let me start with point C. From C, I am going to take a imaginary section like this. It has to start from C, go till here. Let this distance be x. What is the moment produced at this section because of this load? Load into perpendicular distance. Load is 1, perpendicular distance is x. 1x. Now sign convention. Again my same sign convention. If you look at this sign convention, this is acting clockwise and right hand side anti-clockwise is positive. So minus 1 into x. This is the moment at this section. Now right here origin. Origin is C. You are starting from C going towards B. Limits. Limits means distance. At C, distance x is 0. When you reach point B, distance x is equal to 3. So limits are 0 to 3. Mx, moment at this section. Forget this part of the frame. Consider the section here. So moment at this is 1 into x minus x. EI values as it is I. EI. Now consider this section BA. This section. So what I am going to do is I am going to start from B, go towards A. Let me take a section here at distance x. Now let me write the bending moment equation. Here for this section, origin is B. Limits means distance of BA 0 to 4. Now moment at this section. So here you have to consider two things. One is this couple, another is this point load. Moment at this section because of the point load is 0, because perpendicular distance is 0. This point load is acting through the beam. Now couple. Now to consider the couple, what you have to do is look at the sign convention. You have to look at beam in this direction. When you are looking at this direction, right hand side, anti-clockwise is positive and this couple is acting clockwise. So minus 3. Distance does not come into picture. For couple, you have to take the values directly. So its value will be minus 3. EI, 2I. Hence you write here 2EI. Now let us write the strain energy equation. So strain energy is what? Integration of 0 to L m square by 2ei dx. Now here I have to write the equation two times, once for BC, next for CA. So I can write strain energy is equal to strain energy of BC plus strain energy of BA. Now let me go on writing the equation. So strain energy for BC, sorry, BC or CB. For this integration, first substitute the limits 0 to 3, m square, m you have to take these values, minus x bracket square divided by 2ei dx plus for BA limits are 0 to 4, m is minus 3 bracket square divided by 2 into 2ei. 2ei is there, 2 into 2ei dx. Simplify this, 0 to 3, minus x square is x square, minus 3 square is 9, plus 9. So x square by 2ei dx plus 0 to 4, 9 by 4ei. 2ei into 2, 4ei. Take the constants outside. 1 upon 2ei integration of 0 to 3 x square dx plus here 9 by 4ei, whole is constant, so here remaining will be x into dx. One into dx. Now integrate them. 1 upon 2ei integration of x square, x cube by 3, 0 to 3 plus 9 by 4ei, actually 9 by 4ei 1, integration of 1 is x, 9 by 4ei x 0 to 4. Now substitute the values. 1 upon 2ei x cube, so 3 cube by 3 plus 9 by 4ei x into 4 or into 4. So substituting the values, you get 3 cube is 27, sorry it is x square, okay, take it. So substituting all the values, you get 13.5 by ei. This is the equation 1. So simplify all these things, you get these things, 13.5 by ei. Now work done. Work done is what? Half P into delta, where P is applied load, 1 into delta. You get the equation delta by 2. Let that be equation 2. Equating work done to strain energy, delta by 2 is equal to 13.5 by ei, or delta is equal to 27 by ei. This is the equation. Delta is equal to 27 by ei. Now let me find the values of ei. Ei is equal to, E is given as 200 kilonewtons per mm square into I is 30 into 10 raised to 6 mm raised to 4. Now I want the values in kilonewton and mm. So first multiply these things. 200 into 30 into 10 raised to 6. You get kilonewton mm square. I want to convert this into meter square. 1 mm is 10 raised to minus 3, 10 raised to minus 3 square. So 200 into 30 into 10 raised to 6 into 10 raised to minus 6 kilonewton meter square, or you get 6000 kilonewton meter square. So substitute the values. I have this equation, delta is equal to 27 by EI or 27 by 6000. You get the value 0.045 meters. This is the final value, deflection of point C. Thank you.